Recording is rolling. So this is Tuesday, October 5th. Well, so you guys remember that, centripetal force, that's from your lab last week. And yesterday I started talking about universal gravitation. And today by the end of class, I'm going to bring those ideas together and talk about orbits. So that's sort of our roadmap. Okay. This was my ambitious plan for today. I'm not going to have time to do everything I wanted to do, but we'll at least get the story rolling. Picture retakes. So here's picture retake schedule. Looks like we're on letter S. If your last name starts with an S and you need to retake them, go ahead sometime and head down and get that. My starter question is, say we're looking at the moon, which has this mass, this radial size, and hey, here's the universal gravity constant that I introduced to you guys yesterday. Can you figure out what's the free fall gravity, what's the orbital speed, and what's the escape speed? Now, actually, I haven't even told you guys how to get those values yet, but later on in this class, we'll actually answer all these questions. So be looking for that, because that's eventually where the story is headed. Okay. One more thing I want to mention before I get rolling with the physics. Right. So you guys know that we're near the end of the quarter, end of the first quarter, and at the end of this week. Right. So you guys' quizzes, I'm still waiting on a handful of late quizzes. I want to get those back to you guys. I'm ready with the solutions. All I have to do is press a button and the solutions will post to Classroom, but I need to get all the quizzes in first. Once I get all the quizzes, I can post the solutions. I can give you guys your quizzes back. You guys can do corrections for half credit back. But that's probably not going to be the end of the quarter when I have to post all my grades. So here's what we'll do, because I see a bunch of you guys have like 89s and 79s. So you guys remember that there was a bonus homework assignment? I know there's a new one too. There's a new bonus homework assignment, so I think it's worked out pretty good. So this is the new stuff. But there was an old one for your forces. And what I did is I went back in the gradebook and instead of made it 20 out of 20 points, I made it 20 out of 10. So there's actually like real like 10 bonus points going around there. If you already turned that in, like you already did the bonus for forces, then you just got 10 extra points. So bump up your grade about a point overall. If you need a little extra credit, got a few days, if you go back and do that bonus homework for the forces and turn that in, then I will go put that in. So you've got about 3 days to do that if you want to take advantage of that. Right, so back to the story. Gonna very quickly whip up some notes that you guys saw at the tail end of yesterday, just to remind you guys how stuff's working. Suppose there's maybe like a planet and its moon, or maybe a couple of asteroids. I'm gonna call them mass big M and little m, and they're separated by some distance, a center to center distance. So I'm going from the center mass to the center mass. I'm gonna call it distance r, and because masses gravitationally attract, or at least that's the Newtonian perspective, then there's a force, and remember, those forces are equal, right? It's equal forces, says Newton's third law. The masses are different, therefore the accelerations are different. But what is the value of that force? Well, you multiply the masses together, divide by the distance between them squared. There's an inverse relationship between force and distance. And then multiply that all by a universal gravity constant. You guys remember all this? And that universal gravity constant is it's a very, very tiny number. 6.67 times 10 to the minus 11 meters squared per kilogram squared. That's like 0.000, just like a string of zeros before you even get to any digits. This number is so small. That's what that exponent means, right? Remember? What can you do with that? Well, you can take this to switch perspectives a little bit, down to a planet, just a single planet. You can also use that expression to determine your own weight. Okay? So maybe the planet you're on has some mass, capital M, you have some mass, little m, and there's a radial size between you and the planet called r. Sometimes I switch to capital R if I'm talking about a fixed radial size, so maybe like this case. Okay. So from a cosmic perspective, like, what is the distance between you and the Earth? Like if I asked you guys, say like before you ever walked into physics, what's the distance between you and the Earth? You might say, well, there's no distance. I'm on the Earth. Okay. From a cosmic point of view, the distance between you and the Earth is the radius of the Earth. Why is that? Because all the mass below you in elevation, which is the entire mass of the Earth, except for like mountains, right? we're going to assume is concentrated at a single point at the center of mass of the Earth. So here's your mass, here's the Earth's mass, and you guys see mathematically it's all concentrated at this point, which is actually pretty close to mathematically how it works out. I mean, everything to your right and to your left cancels out, and then some sand particles are closer to you, some sand particles are on the opposite side of the Earth, right? And then mass of the planet, we're going to treat as a single point mass. So your weight is equal to gmm over r squared. Hey, that's the formula that we were just doing. It's the same thing. But then I can take this and I can do something else with it. I remember that acceleration is equal to a force acting on a mass. This is Newton's second law of motion. Second law of motion. Forces cause accelerations. So if your weight is a force, then say we were to hop off a ledge, I wonder what your free fall acceleration would be. Oh, well, it would just be this expression divided by, hey, your mass. That would look like this. Free fall gravity, which is type of acceleration, is equal to gm over r squared, where the only m in this, the only mass in this equation is the mass of the planet. Notice that whatever is accelerating at the surface, that little tiny point mass little m, cancels out. But you know that to be true because that's the Galileo story. Galileo dropped in different masses from the Leaning Tower. They all fell together. Right? Or you guys even did this as an experiment. You remember your cars going on those inclines? The mass of the car did not affect its motion. Okay, okay, let's start to combine these ideas. Take this gravity idea and rotation, start to put this together. So Isaac Newton had this interesting thought experiment. We call this Newton's cannon. Okay. And it's going to lead to circular orbits. Maybe I shouldn't have written that yet because I'm sort of spoiling the story. But it goes like this. So you got a planet. And maybe this planet has a ridiculously tall mountain on it. In fact, this mountain is so tall, it actually goes above the atmosphere of the planet. So we're getting above the drag force from the atmosphere. So like, no drag. Side note here, how thick actually is the atmosphere of Earth? Well, it's a few hundred kilometers thick, which might seem like, okay, a few hundred kilometers, that seems a lot, right? But that's actually really small compared to like the millions of meters, like the thousands of kilometers of the radial size of the planet. You guys ever heard if the Earth was the size of a basketball, you cover that basketball in like plastic wrap? That plastic wrap is about the thickness of the atmosphere. Right? So pretty big, thin in big scheme of things. But back to Newton's cannon, we're going to park a cannon right on top of that ridiculously tall mountain that's above the atmosphere. So we're above atmospheric drag. And we're going to start firing cannonballs. Ooh, this looks like a projectile problem, doesn't it? Projectile. You guys know projectiles, there's only one force on any projectile, or anything that's in free fall, and that's its own weight. And I usually call weight mg, but let's think about our new way of thinking about weight, the more universal point of view, which is gmm on r squared. Okay. What I just wrote in red ink, that is the free body diagram on that cannonball, isn't it? Now for projectiles, you guys have seen enough of these. You know, if you park a cannon on top of a cliff and you aim it horizontally, just like in this picture, the cannonball will eventually hit the ground. Okay. But we've always been assuming a flat Earth, which is approximately true as long as you're within some locality. Okay. But if you get big enough, then that starts to go out the window. Like if you assume a flat Earth, you can make a map of like the state of Florida, and it's all fine and good. But can you make a flat map of the entire world? Well, not without some distortion. And then we're like, well, that's like a Robinson projection or a Mercator projection, right? There's like some trade-off. Okay. So what if you got this cannonball going so fast, some speed v, that the amount that it fell vertically due to its weight as it was being pulled around also equaled the amount of that the ground beneath it changed due to the curvature of the Earth. So it's like falling around the curve of the Earth. You guys remember if you drop something from rest, it falls about 5 meters in the first second of falling? Right? Or if you blast something horizontally, same story. Right? But what if it's going so fast to the side that 5 meter drop off exactly was the same as like a 5 meter change in curvature of the Earth. Ooh, then you would actually reach orbital velocity or orbital speed. Right? You could send that cannonball in orbit around the Earth. Right? Isaac Newton realized that this is exactly what was going on with the moon. He was the first person to recognize that, or at least the first person to write this down. Right? This is for some radial size r.
So is that why the moon doesn't just crash?
That's it. Yeah, that's why the moon doesn't crash. See, if you started the moon and the Earth from rest, if you started from rest, they would just crash into each other, wouldn't they? Right. Why don't they? Because the moon is in motion. And then, does this look a lot like your guys' lab from last Thursday, Friday? You had a Play-Doh canister, and well, the force was being provided by the tension of the string, which was provided by that hanging weight. But in this case, it's just the weight of the cannonball itself, but same idea. Right? It's got a centripetal force. Centripetal force is its weight. Let me make that note over here. What I just said, centripetal force for this example is being provided by the weight of that cannonball. Right? Remember that centripetal force is never a lone force unto itself. Oh, yeah.
The video you showed us of the guy getting pressed against the wall because of the force, how does that translate to the moon? Like, what would you?
Oh.
Obviously, there's not. Like,
Yeah.
We've sent people to the moon, like, fly on.
Mhm. Yeah. Okay, so the guy inside the centrifuge, yeah, if you're sitting inside a centrifuge, why would you feel like you had like so much extra weight? Well, because there's a back wall at centrifuge that's actually pushing you into a circle. So that all that extra force makes them feel really heavy. The idea is that say got like a centrifuge, got some arms, got like a box here, got a guy sitting in it. There's if this thing's in motion, he's moving really fast to the right, so I'll call it V. Okay? And if there was no walls of the centrifuge box to hold him in a circular orbit, then he would just, first of all, motion, just keep going in a straight line like this. Right? He would fly off like that. Right? But there's a back wall that's pulling him into a circle, that's preventing him from going along this line. It's actually pushing him this way. And that's the extra force that he feels.
So without the wall, you just don't feel it.
Well, yeah, but if you took the wall away, like you had him spinning and then just took away the wall, he would just fly off in a straight line. Like this, you just go fly like that. Yeah, right. He would immediately just feel back to like normal Earth weight.
Is it somewhat of a normal force off the wall?
Yeah, normal force from the wall. Yeah, that's what it feels. Yeah, so that's that. Okay. Now in this case, yeah, if you guys see this is eventually going to become satellites, right? It's going to become satellites. Okay. For example, International Space Station. And if you're inside the International Space Station, you actually feel weightless, don't you? Okay. You feel the same as like if you jumped off a ledge. So there is a force on those astronauts, but that force is putting them into free fall and it's actually keeping them along this dash line path. Okay. Actually, up at the International Space Station, the gravity field of Earth is about 90% of the strength it is down here at the surface. It's not a whole lot different. It's about 90%. Okay. So there is actually a gravity force up there, but they're just in free fall around the curvature of the Earth. Okay. Let's do the math on that. So, I remember what I was saying, was that centripetal force is never a lone force unto itself. It's always provided by one of your classic forces. In this case, weight, right? Like this red force vector. Right? But it could be tension in a string, it could be a normal force. We have expressions for each one of these. Centripetal force is mv squared on r. Right? And if that's being provided by a weight, and remember, our new way of thinking about weight is, here's the universal form, gmm over r squared. Okay? If those are equal, then we'd be solving for a circular orbital velocity, and that's what we're going to do right here. What do you guys see is going to cancel out on both sides? Yeah, I see that. The little m is going to cancel out. Remember, that refers to maybe the mass of the cannonball or the mass of the satellite when we get to it. Also one of the r's, yeah. Not completely, but partially. Now, speaking of the m cancel out, I know we haven't exactly answered this yet, but we haven't found the solution to this question. But suppose you're in the International Space Station. It's going at some speed that we're about to figure out what the expression for that is. And now you get a bunch of new supplies. So there's been a delivery, there's new supplies, there's new astronauts to increase the mass of that International Space Station. Do you have to make it go faster to keep in orbit? No. And you know that right here because the little m cancels out. So whatever orbital speed is has nothing to do with the mass of the satellite. Okay? What is the orbital speed? Well, there's only one object set. It's square root of both sides. Equal to this expression right here. Square root of g m on r. That's it. That is the speed you have to go to maintain a circular orbit around the planet. All right. You guys good there? I'm going to tell you guys one more detail that okay. So I usually teach this class in a little bit different order, and I've usually done conservation of energy by the time I talk about this. And the reason I'm bringing that up is because there's another speed I want to tell you guys about, a very special speed called escape speed. Okay? That's to say that how fast you have to get a rocket going to blast away from the planet and fly away just from its own inertia, like this rocket. How fast is that? Call it the escape. Okay. And just take my word for this that this is true now, and I'll prove this to you guys when we get to conservation of energy, because it looks very similar to the speed. It's the same thing, but I'm going to slip a 2 underneath that radical. So square root of 2 times gm over r, like that. Okay. So now you have expressions for how fast you have to go to stay in a circular orbit. Okay. And if you speed up even faster, how fast you have to go to break away from the gravity of the planet and fly away forever. Yeah, Eddie?
I have two questions. One is that V-escape related to that car problem we did yesterday with the V-Max of it about to drift off the road? Is that the same V-escape?
I think it's no, that's a different type idea.
That's a different type?
Yeah.
Okay, and the second question had to do with the International Space Station. Are they going at V-min for the orbit velocity? Is that why they're weightless? If they went any faster, like approaching escape velocity, would they actually feel weight in the inverse direction of Earth?
Okay, so yeah, if you're in a rocket in orbit, yeah, you do feel weightless, just like in free fall around the curvature. What if you were to speed up? Well, during the speed up process, if there's an acceleration involved because you're speeding up, then you would feel that there would be some net force. You might be able to like stand on the floor and feel really light while it's speeding up. Okay, now once it's done speeding up, and you like cut off the engines, you're back in free fall, then you feel weightless again.
So it doesn't matter how fast that V orb is.
Right.
You still feel no weight up there.
Yeah, true. Remember how you don't feel speeds, right? Right. So speeds are always relative. Right? You can feel changes in speeds caused by forces. Okay. Yeah. So you got this. The other thing I wanted to say about escape speed, there's a few things I want to say. So here's one thing: is that because there are going to be some misconceptions about escape speed. Escape speed is the speed you need to get up to such that you could cut off the engines of this rocket and just based on its own inertia, it could still get away from the planet. Like if the engines are cut off and it's kind of close to the planet's gravity is going to pull it back and it's going to keep slowing down. But if it's going at least the speed, it'll have enough speed that it can actually fly away forever. The other thing about escape speed is that you don't actually have to reach the speed to escape the planet. You can actually go slower than this. The catch is that the engines to the rocket have to be blasting to do that. For example, here, I'll give you maybe kind of an intuitive example. It's kind of ridiculous, but what if there was a rope ladder from the Earth to Mars? Just run this crazy example. Do you guys think you could climb that rope ladder, like rung by rung by rung, and eventually make your way all the way to Mars? Yeah, right? Getting nowhere near this escape speed, right? This is probably a ridiculous escape. I mean, take a baseball and throw it straight up. It's going to be nowhere near this. It's just going to fall back to Earth, right? Yeah, you can actually get away from the gravity of the planet going slower than this, but the catch is that you have to be constantly supplying a force, right? But if you want to cross the engines and just escape with inertia, that's what that speed represents.
So if I were to take like a manhole cover and see nuke under it.
Yeah, somebody going to the moon. Yeah. All right, so back at the top of class, I asked you guys what were, where's the, here it is. What is the gravity field, orbital speed, and escape speed for the moon? Let's crunch those numbers now for the moon and also for Earth. I'll do both of them with you guys. Let's do the moon and also Earth. Okay. Let's actually start with Earth. It's probably more relevant to us. So our planet. So here's the mass of our planet. 5.98 times 10 to the 24 kilograms. Woo! Right. Here's 1 kilogram. if I had this many of this, that would be our planet. Here's the radial size of Earth, 6.38 million meters. You guys know 10 to the 6 is million. And also you have to know universal gravity constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared.
Does it matter when you're talking about the radius? Sometimes you use a capital R.
Oh.
Like a lowercase r.
Yeah.
Does that matter?
Okay, so that's one of those weird habits I've had. Sometimes I use capital or lowercase r interchangeably. What I try to do is use capital R for fixed values like radial size of planets, and a lowercase r for maybe something that's more variable. Like for example, there are different orbits that you can park satellites in. Low Earth orbit is actually pretty close to the radial size of the planet anyway, so we're gonna do something assuming that. Right? But there are other places that are good to park satellites. One counterexample to this could be something like what's called a geosynchronous orbit. You put a satellite way the heck out here and have it orbit Earth so that its orbital period is 24 hours. You guys see the advantage of having a 24-hour orbit because if you're down on the surface, you can look up and that satellite would appear stationary compared to the planet, wouldn't it? So a lot of weather satellites are parked in that orbit. Okay? But low Earth orbit, it only takes about 90 minutes to go around the Earth, which is what we're going to do right here. Okay. So what is the gravity field on Earth? What is the orbital speed? Let's say in low Earth orbit, so near the surface, get just above the atmosphere. And then finally, how fast do you have to go to cut off the engines and still escape the planet? Start with gravity. Here's the expression for it, gm over r squared. And the numbers go 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, multiplied by the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, all divided by 6.38 times 10 to the 6 meters, and then square that radial size. Now, part of the trick this week and next week is figuring out how to communicate this to the calculator. I see scientific notation all over the place. I see fractions. I see expressions being squared. Okay? And then when we get to these other questions, there's going to be square roots also. So make sure you can plug these numbers correctly into a calculator. That's part of the trick. Okay. So 6.67 times 10 to the negative 11, close that. I should mention this too. I think you guys have probably figured out by this point in the year anyway, but you guys know that this model calculator on your desk has two minus signs, and they mean different things. And the calculator treats them differently. So the one on the right side is a subtraction function. The one on the bottom in parentheses is a negative sign, and that's the one you have to use right there. Okay. Otherwise, the calculator gets confused. Okay. Also, this calculator knows close open means multiply, so that's nice. 5.98 times 10 to the power 24. Close, divide by open, 6.38 by 10 to the power 6, close square. Okay. Now, as soon as I hit enter, you guys know what number is about to pop up on the screen. What number? There you go. Oh, yeah. 9.799. Let's call it 9.8 meters per second squared. Oh, yeah. Look at that. Yeah. All right, so thank you. All right, so the other two questions were what's orbital speed and escape speed? So I remember orbital speed was square root gm on r. Drive that for you guys. Okay. I'm not going to write all the numbers in there, but I will punch this in the calculator. Now, there's different ways to put this in the calculator. One way is you could chunk this down to smaller parts. I'm going to put it all in one go. And what I'm going to do that is this. It hits second square root. So square root in the calculator gives me that parenthesis. Okay. Let me do something that's wrong. Pay real close attention, see if you see what's wrong. So g, 6.67 times 10 to the negative 11. Got mass of the Earth is 5.98 times 10 to the power 24. Close, divide by open. Radial size of Earth, 6.38 by 10 to the 6. Close. Right. Now, the way I type that in, I'm going to get the wrong answer, but I'm doing this intentionally because this is a common mistake that I see students make. Okay. Let's see what number I get. Whoa, 7 times 10 to the 12. That's ridiculously fast. Actually, it's faster than the speed of light, isn't it? Yeah. Okay. So that's definitely wrong. Although, well, yeah, you're definitely escaping there. What did I do wrong? Get faster than the speed of light.
You closed the parentheses in the wrong place.
Boom! Exactly. See, as soon as I close that first parenthesis, what the calculator interprets that this model calculator is it stops square rooting. So the only thing it square rooted was that G, and then I lost the M and the R inside the radical. The way to fix that, I can fix that very quickly. Go back to the beginning, hit second insert, open up a ridiculous number of parentheses, and now for sure everything is underneath the radical. This model calculator automatically closes all the excess ones at the end. Not all calculators do that. This one does. I like it. Second insert. So second, and then the delete button above it says insert, and then you can just start punching in extra parentheses. So the number is 7,907 meters per second. There you go. So just above the atmosphere, like International Space Station, low Earth orbit. If you send it that fast horizontal to the surface, it will stay in a circular orbit. That's it. How about?
I'm sorry, I don't know
Oh.
how to do this calculator.
Okay. So let me zoom in here. Okay. So suppose that you had only one parenthesis, and it's like, well, that's not enough. Hit second, and then see this delete button, but above it says INS, like, it's not immigration natural selection, it's a insert. Okay, so second insert, and then you can start doing open parentheses. And then now it's for sure grouping everything underneath the radical.
Okay.
All right, there you go. Now I know escape speed is a very similar looking formula. Like I said, I haven't derived this for you guys yet. You guys are going to learn this in the future, how to do that. It involves conservation of energy. But do you guys see that escape speed is orbital speed multiplied by what? Square root of 2. Is it? So if I have one of these, I can very quickly get the other. Okay? I'm just going to take this and multiply by the square root of 2. Right? And get, yep, that's the answer, 11,000 some meters per second. Okay? So if you got a rocket going straight vertically at that speed, it'd be moving just fast enough to break away from the Earth and fly away forever. That's, you get up to that speed and you cut off the engines. They'll have enough inertia. Okay? It can get to like the edge of the universe before it slows down to a stop. Guys good? Hey, let's run these numbers for the moon. Wait, let me see how we're doing on time. Got that. You should see all the other stuff I need to tell you guys. Oh. Okay, I think we're good. Okay, you guys ready for the moon? We're gonna do the same thing, but for the moon. The moon. The mass of the moon is 7.35 times 10 to the 22 kilograms. Pause right here. Let's do a side-by-side comparison. Here's the mass of the Earth. Here's the mass of the moon. You guys see those two numbers? Just the first digits are kind of close to each other, like 7 point something, like almost 6. Let's call this 6 and this 7. That's basically the same number, pretty close. So the difference between the mass is really comes down to order of magnitude, doesn't it? 10 to the 22 versus 10 to the 24. So based on that, the Earth is how many times more massive than the moon? 100, because it's 10 to the 2, which is like 2 decimal places, that's 100 times. The Earth is basically almost 100 times more massive than the moon. Radius size of the moon, 1.74 million meters. And remember, the Earth was also order of magnitude of some millions of meters, so it's really similar order of magnitude in terms of the size, like the radial size, but the mass is off by a factor of 100. Interesting. Universal gravity constant, 6.67 times 10 to the minus 11. Bunch of units. Okay. And same questions as before. What is the gravity field on the moon? What is the orbital speed, say in a circle? And what is the escape speed? Like how fast do you have to go to fly away from the moon? Okay. I'll just write the formulas that you guys already know here. The orb. And the escape. which is, ooh, I'm gonna use a fancy version of this. You say square root of 2 times b orb. How about that? It's kind of what we did before anyway. Right? Let's see how these numbers are gonna play out. Just do it on the calculator. So 6.67 by 10 to the negative 11, close, open. Mass of the moon, 7.35 by 10 to the 22, close, divide by, open. 1.74 by 10 to the 6, close, square. Before I show you guys the answer, remember how this number was 9.8 meters per second squared on Earth? Let's see what it is for the moon. 1.62 meters per second squared. Or sometimes AP will write it this way. 1.62 newtons per kilogram. If you ever see newtons per kilogram, same thing as meters per second squared. Let's see what's orbital speed. So back during the Apollo missions, usually they had a couple astronauts run around on the surface and then one guy in a vehicle going in orbit around the moon. I wonder how fast that guy was going. See, square root of, I know what happened before. I closed the parentheses too fast and that ran me into trouble. It's going faster than the speed of light. So I'm gonna open up more parentheses, make sure I for sure group all the stuff under the radical. We got G 6.67 by 10 to the negative 11, close open. The mass of the moon, 7.35 by 10 to the 22. You guys get to practice with the calculator, right? So you can put this in, get the same numbers I'm getting. Divide by, open, 1.74 by 10 to the power 6. This calculator will close all the excess parentheses for me. Now, remember what orbital speed was for Earth? It was almost 8,000 meters per second. Do you guys think it's going to be more or less for the moon? Probably smaller. Would that make sense? I mean, it's a little tiny, right? Hey, what? Yeah, it is smaller. 1679 meters per second. Remember, the Earth was about 7,900. For the moon, it's about 1,700. So that's a lot smaller. You don't have to go as fast to orbit the moon. And then, well, you guys know how to go from orbital to escape. You just multiply by the square root of 2 because you're off by that. Right? So times the square root of 2. It looks like, okay, so now we've got, let's say we got this situation. The couple astronauts on the surface jump back in the vehicle and they blast off and they meet the guy that's in orbit and they all get together. And now they're ready to go back to Earth. So they fire up the engines and they get up to this speed right here, 2,300 and some meters per second. And once they get to that speed, now they can cut the engines and coast back to Earth. All right, all good? Oh, yeah.
Will we ever be asked to find M in
Yeah.
acceleration? Okay.
Could be. Yeah. So I'm doing some classic fundamental type questions for the guys, but you totally could be given some of these other values and be asked to find something like that. Actually, that would be a really good question. That's how the masses of some planets are discovered. Say, like, if you see Jupiter and you're wondering, what's the mass of Jupiter? Now, we know what the mass of Jupiter is, but how do we know it? We know it because we see its moon in orbit. So that's actually a really good question. If you see the moons in orbit around Jupiter, and you know how far away they are, and you see how fast they're going, you can back calculate what the mass of Jupiter is. And same thing with all the other planets. Actually, the mass of Pluto, we never quite knew. There were different estimates for it because it was just like a fuzzy blur at the edge of the solar system. Until scientists found that it had a moon orbiting it, I think called Charon, I think? Right.
Charon.
Charon? Is that how you say it?
Charon by Roman, yeah, it would be.
Yeah,
That's
okay.
the riverboat man.
Right, so, all right, about that then, Charon. And when they figured that out, they could do a little bit of geometry, and that's actually how they back calculated the mass of Pluto originally. That's how you do it.
And then another question, is there a delta R between big R and little r? And would that affect the rate change in velocity if I dropped my from about like 1,000 meters above big R? Would I have to like find the rate change in velocity ever? Or is that
All right. Yeah, you're getting some stuff that I wanted to get to today, but probably have to talk about tomorrow. So yeah, you guys see this G of, well, for Earth, you guys know that number is 9.8 meters per second squared. Yeah, if you want to be strict about it, this is really only true at the surface, isn't it? Okay. Like if you had a ridiculously tall, like Newton level mountain, right, then do you think this number gets less and less the further away you get from Earth? How about this? What if you tunnel into the Earth and you get towards the center? Right? I mean, this number would also change, wouldn't it? By the end of class today, I'm going to give you guys some stuff that's going to start to set up that story. Yeah, and we're going to think, because this number is really only true at the surface. But you're right, it does change depending on your elevation. So I'm going to do 2 more things with you guys. Got just enough time to do this. So let's put all these speeds together and think about the big picture of how this works. One of the things I want to talk about, it's going to have to wait till tomorrow, is Kepler's laws of planetary motion. So here, if you have let's just talk about a satellite in circular orbit around the Earth, for a little satellite here. Okay. Then you know that this orbital speed, the orbital, for like a circular orbit, is square root g_m on r. Right? So you know that. Okay. But here's the problem with that, something like that, is that's a very fragile situation, because if you went like a smidge slower, would you just crash down to the ground? Okay. Actually, pretty much all satellites in low Earth orbit eventually will, given enough time, like hundreds of years, because the upper particles from the atmosphere collide with them and slow them down a little bit, they'll eventually crash. Okay. So wouldn't it make sense actually to go a little bit faster than this? If you go a little bit faster than this, you're no longer going in a circular orbit, you're going in a what shape? Elliptical. Yeah, it would make an ellipse. Okay. I'm going to do an activity with you guys too that we can actually make an ellipse, but save that for tomorrow. So this speed would be between orbital speed for a circle and escape speed if you get going fast enough. And of course, if you do get going fast enough, then you eventually reach escape speed. If you're directed away from the planet, going at least this fast, square root 2 g_m on r, then now this path is definitely not elliptical, because that would loop back around. Okay. So here's a circle, here's an ellipse. So I got a circle, here's an ellipse. What shape do you think this path is following? Starts with an H. Hyperbola. Yeah. Side note here. Do you guys remember a news story from I think like a year or 2 back? Some weird shaped object called, I think they call it Oumuamua or something. That you guys remember?
I think I've heard that name. Wasn't that a unidentified object that was
Yeah.
on Earth for a while? We thought it hit the planet, but it didn't.
Ooh, I'm gonna tell you guys the story tomorrow. Let me add this to my. I'm gonna tell all my classes the story. All right, yeah, we're gonna save that one for tomorrow. But telling you guys about that reminds me of that. Right, so here's the last thing I can fit in before the bell, and what I'm about to show you guys is going to set up more stuff we're going to talk about tomorrow. So let's suppose that we're astronauts flying around the galaxy, just exploring different planets, and we come across this one planet, and from the outside, looks like a normal planet. It has some radial size r that's measurable, so it looks all fine and good. And then we jump down this planet and start walking around, and that's when we notice there's something kind of funny going on. We say, well, I know that the gravitational force should be g_m over r squared, but I feel very, very light. Like there's hardly any gravity for a planet this size. This planet has hardly any mass. And so we get to investigating, and we break out the shovel that we brought along in our space rocket, and start digging a tunnel. But we don't have to dig very far before we realize exactly what's weird about this planet. This is an eggshell planet. It's completely hollow. This is a hollow eggshell planet. Not like Earth. Okay. And then, now, keep in mind, you can walk around on the surface. Everything's perfectly fine. But we have this idea. I want to jump in that hole. And I wonder what's going to happen if you're inside this eggshell of a planet. Make a dashed line diameter. Let's say you're somewhere on the diameter of the sphere that cuts right through the center. Okay. And let's say you're specifically right here. Right? So you're like 3/4 over, or like 1/4 from the right side, 3/4 from the left side. Guess that? So you're sitting right there. Right? I wonder which way you would overall be pulled due to gravitational effects. Like you might think this, you might think, well, maybe I'll drift to the right because I'm closer to all this mass on the right side. Or maybe I'll be pulled to the left because there's a lot more mass to the left. Right? Or maybe everything kind of cancels out. Right? I wonder what's going to happen. Take you guys through this. Here's one way to analyze this. Is I'm going to make a cone like this. Right? And let's compare these distances. Where you are from the left side to where you are from the right side. So your distance to the right side I'm going to call x, and your distance to the left side, well, let's call it 3x, right? Because you guys see proportionally it'd be x versus 3x. You guys see that? Okay. Okay. And then I'm interested in this cone of shell dirt on the right side versus this cone of shell dirt on the left side, which are each approximately circular. Now, all the stuff above and all the stuff below vertically cancels out. So really, which way you get pulled comes down to this mass versus this mass. You guys see that? Okay. Now, this mass on the, I'll call this M sub R, mass on the right side. And this mass on the left side, I call it M sub L, mass on the left side. Okay. Now, it used to come closer to the right side, but there's more mass on the left side. So what's going to happen? Okay. Well, do you guys see that the one on the left side has 3 times the diameter of the one on the right side? Because it's 3 times farther away, and they've got some triangles going on. Guess that? 3 times the diameter. Okay. But this area, pi r squared, the important thing is that the area is proportional to the square of the radial size. It's also proportional to the square of the diameter. Okay. So the fact that it's 3 times the diameter, it has how many times the area? You guys see it's 9 times? Therefore, it has 9 times the mass. Okay. Now, if I compare the force pulling to the left versus the force pulling to the right, I think the bell is going to beat me on this one, but if it does, then I'll finish the explanation a few seconds after the bell, and then this is all being recorded, so you guys can catch some recording. So, what is the force left versus the force right? Okay. Let's compare those. Okay. So, I know the force left is equal to G times 9 mr. Oh yeah, guys, turn in your lab write-ups to the grade tray before you walk out, and I'll just keep recording. I'll record probably another couple minutes here after the bell. Okay. Here's the story. Guys, all the gravity is going to cancel. That's the end of the story. The end of the story is it's going to be a gravity-free zone inside that planet. Gravity-free zone. Gravity-free zone inside the planet. Nope. Well, you're inside. You're floating around inside. Okay. And this is going to set up some story for tomorrow. Okay. So for the video, I'm going to finish this off here. Okay. So let's say times mass of the person divided by this distance 3x quantity squared. The force on the right side is, well, so you got universal gravity constant times just plain mr times the mass of the person, all divided by just plain x squared. Okay. Now, if you compare these two, see at the bottom, if I square that, I pull a 9 out in front, factor this 9 out in front, this 9, I got g mr mp over x squared, and this is just plain g mr mp over x squared. And if you didn't see it before, I bet you can see it now. These times are going to cancel. It's the same force, which means that you're pulled exactly as much left as you are right, which means gravity cancels out. It's a gravity-free zone on the inside. So the takeaway is that any mass that's above you in elevation, that's uniform all the way around, cancels out. And the only gravitationally attracting mass for a planet is mass that's beneath you in elevation. And that will be a setup for tomorrow.